Today we're going to be looking at calculating an electric field due to a continuous charge distribution. Just like in the last video, we're actually going to use the principle of superposition. Here, instead of force, we're going to be using electric field though. Let's just dive right into an example problem. What we're trying to find in this problem is the electric field at point P. There's a ring here, maybe it's a conducting ring, a metal ring, that has a total charge Q on the ring. The radius of the ring is equal to A. And this is a perfectly circular ring. It doesn't look circular in this picture, but you imagine that part of the ring is coming out of your screen and the other half of the ring is going behind your screen. So it's a perfectly circular ring that sits in the YZ plane. If we said that this is the x-axis and this is the y-axis and the z-axis is coming out of your screen. So this is a perfectly circular ring, and we're trying to find the electric field at point P. The way we're going to use the principle of superposition, though, is to divide up this ring into many little charges. We're going to call those little charges dq. So one example of dq is this dq that's at the top of the ring. But there are many other dq's that go all the way around the ring, and each one of the little dq's is going to contribute to the electric field at point P. So the electric field at this point P, due to the dq, can be found with the formula dE is equal to 1 over 4 pi epsilon naught times Q, which is just the dq, over r squared. The r squared we were referring to here is the distance between the charge dq and the point P. That distance is equal to the square root of x squared plus y squared. And notice also something that we'll be using later is that this vector r makes an angle theta with the x-axis. So that'll come in handy later. Another thing that might be useful to us is to actually try to figure out what dq is. How much charge is there in dq? In order to do that, we're going to actually use another variable, lambda, for the linear charge density. This is kind of like a linear mass density. The linear mass density would be m over L. But instead of using a linear mass density, we're going to find a linear charge density, which will be Q over length generally. For this particular situation, lambda is going to be equal to Q over the length of the ring, which will be 2 pi A. Also, because we have a uniform charge density, we can also say that lambda is equal to dq over dl, where we're just saying that the length of this, the linear length, is dl. So if we added up all the little dl's around this ring, you'd get the total length 2 pi A. I'm going to tell you in a minute why it's useful to get things in terms of dl as well. So let's just talk again about the contribution to the electric field by this dq. The electric field, or the little dE, that's produced from this dq sort of looks like this. In other words, if we were to put a positive test charge at point P, that little positive test charge would feel a repulsive force due to the dq at the top of the ring. So the direction of that force on the positive test charge would be indicated by this particular arrow, which I'll call dE, the electric field due to dq. In order to get the total electric field E, what we're going to do is actually integrate and add up all the little contributions of dE due to all the different dq's on the ring. Now going back to the lambda part, the reason that we want to put it in terms of lambda is that it's difficult to integrate dE without having some limits of integration. A good choice of limit of integration would be, okay, we want to integrate everything around this ring. One way of doing that is doing sort of an integral from 0 to 2 pi a. So we're going all the way around the circumference. So that variable will be dl. So we're thinking that the integral will look something like this. Integral from 0 to 2 pi a of something dl. So that's just what we're thinking the integral might look like in the end. Let's take a closer look at this dE. Remember, there are many contributions of dE due to all the different dq's that are on the ring. dE can be broken up into components. dEx is the x component of dE, and dEy is the y component of dE. Notice, due to symmetry, that all the dEy's will end up canceling each other out, because for every dEy down, there is also a dEy up due to a charge at the bottom of the ring. The dEx's, however, are not going to cancel out because they are all going to be in the same direction. So what really ends up happening here is that the electric field, the total electric field, will actually be the integral of all the little dEx components. So that's going to be our goal for the integral. So noticing by geometry that this angle is also theta, that means dEx is really, so what this becomes is the integral of dE times cosine of theta. So I'm just going to continue down here. My E is now equal to the integral of dE cos theta. Now let's look at dE. dE is 1 over 4 pi epsilon naught dq. Okay, this dq, if I rearrange this equation, dq is equal to lambda dl. So now I have 1 over 4 pi epsilon naught lambda dl over r squared, which is simply x squared plus a squared. I'm using a instead of y because here a is the y value, the vertical value from the origin. The cosine of theta is also x over r. So the cosine of theta we're going to write as x over r is x squared plus a squared to the 1/2 power. Oh, sorry, we didn't put in our limits of integration. That's from 0 to 2 pi a. Certain things in this equation are actually constant, including the 4 pi epsilon naught. Lambda is a constant since we have uniform charge distribution. X is a constant. A is a constant. A is the radius. X is the horizontal distance from the center of the ring to point P. And so the only thing left in this integral is actually the dl. So this is going to be lambda over, lambda times x over 4 pi epsilon naught times, also in the denominator is x squared plus a squared to the 3/2 power. That's all times the integral from 0 to 2 pi a of dl. This integral, when we integrate dl, that's like saying integrate 1 dl. So the integral of 1 dl is just L. And that's going to be evaluated from 0 to 2 pi a. So L evaluated from 0 to 2 pi a is just 2 pi a. Okay, sorry I'm running out of room here. I'm going to put this here. So my total electric field then is going to be equal to lambda. Okay, lambda from here is Q over 2 pi a. So Q over 2 pi a, that's lambda times x over 4 pi epsilon naught times 2 pi a over x squared plus a squared to the 3/2 power. Therefore, my final electric field, let's see, some of these things cancel, the 2 pi a's cancel out, and what I'm left with is, for the electric field, sorry I'm skipping around so much, electric field is equal to 1 over 4 pi epsilon naught times big Q times x over x squared plus a squared to the 3/2 power. And that's my final answer for the electric field at point P. In this example, we're going to be trying to find the electric field at point P due to this finite line charge. So maybe this is a wire that has a uniform charge density. We're going to say that it's a positive charge in this case. In order to find the electric field at point P, we need to break up this wire into a bunch of little dQs, d charges. Those are going to be little charges that will affect the electric field at point P. So really I'm going to be using the equation dE is equal to 1 over 4 pi epsilon naught times dQ over r squared. In this case, r is the distance between dQ and point P. So that distance is going to be the square root of x squared plus y squared, where we say the distance from the origin to this dQ is called y. Ultimately, what we want to do is get the total electric field, which will be the integral of all these little dE's. The thing is that dq is a difficult thing to integrate, so instead we want to find an integral that is easier to integrate. I think what I want to integrate is I want to look at an integral from -a to a of dy. So y is going to go from -a to a. So I'm just going to have that in my head that I want to get this integral into that format. In order to do that, I'm going to use the linear charge density lambda is equal to the total charge q over the total length 2a. Likewise, lambda, since it's uniformly dense, is going to also equal dq over dy, where dy is the vertical distance of this charge. There's one more thing that we should notice here, which is that the electric field at point P due to dq we'll call dE. This dE can be broken up into x and y components. If you'll notice, dEy, if we add up all the dEy's from all the little dq's, because of symmetry, all the dEy's will cancel out. That's because for this particular dq, there's another dq maybe down here, which will have a dE that looks like this, and the y component of that dE is going to cancel out this y component of the dE. So really all we really care about is adding together all the dEx's. So really our integral is going to look like the integral of dEx. dEx is the component of dE in the horizontal direction, and if we say that this is an angle theta and this is an angle theta, then our integral will look like dE times the cosine of theta. That's going to be equal to dE times x over r, adjacent over hypotenuse. And since r is the square root of x squared plus y squared, I'm just going to write that in like this. Okay, so now we can plug in for dE. So I'll start down here. The electric field will be equal to the integral of 1 over 4 pi epsilon naught dq. Well, dq, if we rearrange this lambda statement, we get dq is equal to lambda dy. So instead of dq, I can write lambda dy. That's going to be over r squared. Since this is r here, r squared is just x squared plus y squared. Now we can't forget the cosine theta term, so that becomes x over x squared plus y squared to the 1/2. I should add in my limits of integration, so that's from -a to a, now that we're in terms of dy. Let me now take some of my constants out. So what I get is 1 over 4 pi epsilon naught. Lambda is also a constant, equal to q over 2a. So I'm just going to put that in, q over 2a. In this problem, x is also a constant, so I can take that out. And what I have left over is the integral from -a to a of dy over x squared plus y squared to the 3/2. I think what I would do with this integral is just look it up in an integral table, but I think you can also do a trig substitution here. But when we perform this integral, what we get is that the electric field is 1 over 4 pi epsilon naught qx over 2a, and performing the integral we get y over x squared times the square root of x squared plus y squared. That's from negative a to a. We have to plug in those limits for y, because y was our integration variable. And what we get is 1 over 4 pi epsilon naught qx over 2a times 2a over x squared times the square root of x squared plus a squared. We can simplify a little, get rid of some of these things, get rid of these two a's, get rid of one of these x's here, and what we're left with is that the electric field at point P is going to be 1 over 4 pi epsilon naught q over x times the square root of x squared plus a squared. Oh, by the way, this is all in the x direction, so I could just put an I hat there to indicate that the electric field vector will be in the positive x direction. So we can check now that if Q is 0, then this electric field should also be 0, and that's true, so this whole quantity will become 0. We can also check that if x is much bigger than a, then the whole line charge acts sort of like a point charge. So if a is really small, then it should reduce to a point charge. So if a is really small, if this term will go away, and I get 1 over 4 pi epsilon naught q over x times the square root of x squared, which will be x squared on the bottom. So then it reduces to the formula 1 over 4 pi epsilon naught q over r squared, which makes sense. Just using a few checks, we can see that this formula should probably be correct, and we can check that we did the integral correctly. That's it. If you have any questions, please write them down and bring them to class. See you there.